Thanks to the aquarium for hosting this talk. In 1972, hold on, there we go. In 1972, I was a 19-year-old hippie environmentalist in California. And I believed in hugging trees, back to the land, small is beautiful, nature is good, and I didn't trust technology. And I specifically didn't trust nuclear power. Because it was unnatural, it was large, it was corporate, and I associated it with nuclear weapons, which were and still are very scary. And then what happened to me? I had children, and my yes. Oh, this one here. How is it? Better? Okay, or I could yell. So I had children, and there it is. And my son became a climate activist at age 12 and a state representative in Massachusetts when he was 22 years old. And he convinced me that we should all drop what we're doing and work on climate change. That was the issue that mattered. That's the issue his generation would care about and live with, and his children and his grandchildren. And eventually, I decided to do that. So I started studying climate change. I had no idea about nuclear power having anything to do with it, really. But I started to look at how we would actually solve the problem of climate change. And the more I looked at it, the more daunting it became. Today's weather events and fires and droughts and all of that are bad enough, but the real concern is tipping points. Out in the future, we don't know how far in the future, we're not certain when and if they'll happen, but they could bring about events that we couldn't get back from again, a new ice age, a rapid sea level rise much faster than the models predict, and this sort of thing. And that would be Boston under 12 feet of sea level rise, for example. And what if this hit this century, what if it hit next century? Could be faster than we expect, but we know this is coming. This is the future under climate change. Now, I gave this talk at MIT, and the engineers said, well, this is okay because we're on the 4th floor of the building. But that's just how MIT engineers think about it. So the world is not on track to solve the problem of climate change, and you probably know that. But I want to emphasize that we're really not on track. We're way off. It's not just that emissions are rising again last year and the year before in both the US and the world, which is true. But the whole thing doesn't add up because even if we flatten out emissions, we're just stopping the rate at which we're putting carbon into the atmosphere. And that's all that the Paris Agreement would do. The best agreement we have on climate change, if all the countries in the world met their commitments, by the way, almost none of them are, and if they would all add on commitments as they're supposed to come down from this rising line and go to a flat line, that's all we would do is to continue to add carbon at the rate that we already are. If we made Ford Explorers out of carbon and put them in the atmosphere, we'd be putting 15 billion per year into the atmosphere. So that's a lot of carbon every year, and just flattening it out continues to put more carbon in the atmosphere, and it's the amount of carbon in the atmosphere that leads to temperature rise. So when you're putting more in, you're leading to accelerating temperature rise. That's where we're at now. We really haven't made any progress on it at all. World carbon emissions haven't even started to come down. And if you think we're making any progress, I would recommend the new book, David Wallace Wells's book, The Uninhabitable Earth, where he sketches out just how quickly that future is facing my children and grandchildren, if not me. So what we need to do is to rapidly drop the emissions, not just flatten them out. And we need to do this in just a few decades to stay within the 1.5 degree or the 2 degree global warming thresholds that the UN says are critical to stay under. By the way, 1.5 degrees, far less bad than 2 degrees. 2 degrees, way better than 3 degrees. And above 3 degrees, you really don't want to live in that world. So we need to decarbonize really quickly. And nobody's quite got a plan for how to do it. It's really hard to do because more than 80% of the energy in the world is from fossil fuels now. And I focus on electricity in the book because, for reasons I'll explain, partly because solutions to the whole energy system will depend a lot on electricity, and partly because electricity is actually the easiest thing to decarbonize, because it's on the grid, you just need to change how you generate it. Right now, we're generating it mostly from coal. Coal is the leading way that we make electricity in the world. Coal is the fastest growing energy source in the world in the 21st century. So, my book is on Amazon as #1 book on coal. And well, it's true, it is about coal. It's about how we have to get rid of coal. And so I looked for research on how we decarbonize really quickly, and I found this guy, Staffan Qvist. He's the one on the left there. A Swedish engineer who was writing about how Sweden had very quickly decarbonized their system, and that was the genesis of how we got to the book. Now, I want to talk about how much energy we need to really make this work if we're going to solve climate change. When you look at the whole world, I'm an international relations person, so I kind of look at the planet top down, not little pieces that might or might not add up. Look at the whole world. The overwhelming fact of it is the need for vastly large amounts of clean energy, clean electricity in particular, by mid-century when we want to decarbonize. So we started out thinking about today's energy grid, today's electricity grid, and how we clean it up. And that's how most people are thinking. We'll put in renewables and take out coal, and we'll clean up the electricity grid. But that's only a part of the problem. We also need to expand access to people in the poorer parts of the world. They're growing fast. Their energy use is growing quickly. Hundreds of millions of people are rising out of poverty, and with that, using a lot more energy. And this is a great thing for people in the poor parts of the world. People who are grinding sugarcane by hand now will be able to use electricity to do that. People who are burning up in heat waves will have air conditioners. This is all things that people in poorer countries want, and there are billions of people in large poor countries like India and Indonesia that are growing, getting their feet under them, coming up out of abject poverty into sort of lower middle class world lifestyle, and they're going to use a lot more energy. And people in the industrialized countries in the north of the world cannot tell people in India that they have to keep grinding their sugarcane by hand, or they can't have an air conditioner because we used up the world's carbon budget. That's not going to fly. And we also can't tell them that they have to spend 3 times as much on electricity that they could get from coal in order to get it from some cleaner source that's not coal. If coal is the way they can get an air conditioner, that's what they're doing and that's what they'll do. So we need some alternative for that. And we're going to need a lot of it. Now, in addition to that, we're going to need, if we're going to decarbonize the world economy by mid-century, to electrify a lot of things that are now run on fossil fuels, such as cars. So we'll turn gasoline cars to electric cars. We'll turn coal-burning steel furnaces to electric arc furnaces, and so forth. But some things can't be electrified readily, such as aviation fuel. And for those, we'll need to create alternative drop-in substitute fuels that are carbon-free. And without getting into the technical details, the way to do that is to have a lot of cheap electricity, and then you can make a carbon-free substitute fuel. Climate scientists also tell us by mid-century we will need to start sucking carbon out of the atmosphere. We're going to need some negative emissions. Partly that's because they're things that we can't really entirely decarbonize. We need to compensate by sucking CO2 out of the atmosphere. We can do that now, but it's really expensive to do it. And we need to develop better technologies at doing this. By the way, it could also be out of the ocean, which equilibrates with the atmosphere. But in some way, ocean or atmosphere, we need to suck carbon dioxide out. And guess what the key ingredient is to do that? Lots of cheap electricity. We can also desalinate water with cheap electricity and do many other wonderful things. So, all in all, we need vast amounts of cheap, carbon-free electricity in the next 30 years, and the sooner the better. We're probably going to need about 8 times the amount of electricity that the world uses now. So it's really big, really a lot of electricity. With that, we could generate it cleanly, we could actually solve climate change and stay under those critical thresholds. By the way, when I was a young hippie environmentalist, I hated these power lines. And now I'm not sure. It depends what's at the end of them. You know, is there a coal power plant? Then I still hate them. If it's clean electricity, then I like them better, especially if there's an air conditioner at the other end that's keeping somebody in India cool in a heat wave. All right, so where do we get the electricity to do this? Right now, I mentioned, it's from coal mostly and fossil fuel predominantly. And coal not only is the leading source of carbon emissions in the world, by the way, half of it in China, but it's also a great source of disease in the world. When you burn coal smoke, it creates a small particulate particles, matter, that people breathe in and they get sick from it. Cancer, emphysema, horrible diseases. And these diseases kill something on the order of magnitude of 1 million people a year around the world. So that's the baseline. If you want a safe fuel, something safer than coal, just make sure it kills fewer than 1 million people a year in the world and gets 10 times that many people sick who don't die. Other fossil fuels are also unhealthy and dangerous and polluting. Oil tends to explode and to spill. Natural gas, or methane as I often call it, explodes and leaks into the air. And when it leaks, unburned, it's a greenhouse gas itself, 80 times stronger than carbon dioxide. And the carbon-free sources also have their pluses and minuses. For instance, hydropower. Hydroelectric power is just great from a climate change and economic point of view, except that most of the good spots are already dammed and it's hard to expand it. But if you can build a hydro dam, that's great economically, but it does despoil the landscape and occasionally causes lethal floods. The worst of these was in China in the 1970s, killed more than 25,000 people in one day, and possibly 200,000 from famine and disease as a result indirectly. How many of you have heard of that disaster in China? 2, 1? How many of you have heard of the Chernobyl nuclear disaster just less than a decade later? Okay. We'll get to Chernobyl, but it was a lot less than the 25,000 killed by the hydroelectric dam. Solar power also has its pluses and minuses. It tends to blight the landscape, and it produces toxic recycling materials when the solar panels are at the end of their life after 25 years. And in most of the world, there's no plan at all for how those are going to be recycled. Probably they're going to be taken to some very poor country where children will disassemble them and be exposed to cadmium and lead and the toxics that are in them. Wind turbines are a good way to make electricity, but they do chop up birds quite a bit. And solar and wind power are both intermittent. So for instance, here's Europe at night. A lot of lights are burning, but there's no solar power. There's never any solar power at night. And some places for whole seasons. And in fact, my co-author did an analysis of the energy use in Europe that showed that there was an entire week of the year when neither solar nor wind combined produced as much as 10% of their capacity for a week. So there is no solar or wind for a week. So that really gets in the way of relying on those too heavily on your grid, because what are you going to do for the week? If you're in France, I guess go on vacation, but it's a problem. And that brings us to nuclear power. And the thing about nuclear power that's so remarkable is that it's incredibly concentrated. If you take a pound of coal and turn it into electricity, you can power your house, American-style house, for about an hour. If you take a pound of nuclear fuel, you can power that house for 2 years. So it's just far more concentrated. And this South Korean reactor will produce enough electricity for 1 million US-style homes from this little building. So that's very concentrated. It also means it's tens of thousands of times less mining and processing of material. All the inputs are tens of thousands of times less than for coal. And what fits on a truck in this nuclear reactor would take 25,000 railroad cars if you did it with coal. In the book, we compare a Swedish nuclear plant with a nearby German coal plant, some roughly similar size. And the nuclear plant takes a few truckloads of fuel, and the coal plant requires a 5-mile-long coal train every day. If you made coal out of elephants and marched them into the coal plant, you'd need 10,000 elephants per day. So, and then on the waste side, of course, it's a similar story. Coal waste, 50,000 times more than nuclear waste. So it's very, very concentrated, nuclear power is. And even more concentrated than solar panels are, which are actually less concentrated than coal. So looking back at this picture of the solar farm in France, if you took this all the solar panels you see here and multiply them by 3, and then multiply that by 10, and then multiply it by 10 again, 300 times bigger than all that you see, that's equivalent electricity production to what this building produces, except this building produces day and night, all seasons, any kind of weather, the solar comes and goes. The other great thing, in my mind, the greatest thing about how concentrated nuclear power is that it can scale up very quickly. And what do we need right now to solve climate change? Clean electricity that can scale up really quickly at large scale. And that is because it's so concentrated that you build a reactor, you get a vast amount of electricity out of it. It also happens to be the safest of all the fuels. If you look over the history of the last 60 years, vastly safer than coal. Remember, coal, 1 million people killed over every single year, and nuclear power, 400 times safer in terms of lives lost per kilowatt hour generated. There's almost 400 commercial nuclear reactors operating worldwide, and about 100 of them in the United States, where nuclear is the largest source of carbon-free electricity. In the world, it's second only to hydroelectric power. Like any power source, it has its ups and its downs, and one of the big downs of nuclear power is it freaks people out. Everybody's scared of it. And after decades of anti-nuclear propaganda, there are a lot of people out there saying, oh no, we can't use this very concentrated, safe form of carbon-free electricity to solve climate change because it freaks us out. It's too dangerous, it's too scary, we don't like it. And if you think you have the luxury to say that, then you haven't read the book on the uninhabitable Earth that tells you the alternative if we don't solve climate change. And it's the wrong standard to think that nuclear power should be perfect or we don't use it when all the other fuel sources have all their problems and difficulties. The comparison here is not nuclear versus fairy dust that lights up the whole world without ever having any problems and is practically free. It's nuclear power versus other fuels, and specifically coal. In terms of safety, in 60 years of the nuclear industry, we've had one serious fatal accident at Chernobyl more than 30 years ago. And that was the result of mistakes by a government that doesn't exist anymore, the Soviet Union, using a reactor type that nobody would build today. It didn't have a containment vessel to hold radiation in case of an accident. And the government tried to cover up the accident and didn't take precautions that could have helped people to shield themselves from radiation. It killed something like 50 people and then released radiation that might cause a long-term increase in cancer deaths. Now, the UN agencies all raced in there and did voluminous reports to figure out what the effect of that radiation was, and their answer was it might be as many as 4,000 people that die from radiation at Chernobyl. The only thing is that's about the number of people who die every day from coal in the world. This is one accident in 60 years. Sometimes I think if there were more accidents, we would normalize them and we'd get used to the fact that nuclear power is very safe. But when almost nothing ever goes wrong, one accident really freaks everybody out. The Fukushima accident in 2011 in Japan was caused by an earthquake and tsunami that killed 18,000 people, the fourth worst earthquake in history, and a 50-foot tsunami. It wiped away everything, whole settlements, whole infrastructure, and it also damaged this nuclear plant. Now, the problem was not actually the plant, it was the design of the site where the backup generators were all located on low ground together with too low of a seawall. There's another Japanese nuclear plant, the Onagawa plant, closer to the epicenter, same tsunami, same earthquake, but a bigger seawall, and they were fine. Nobody was hurt, no radiation was released, everything was fine there. This plant, badly designed site. And it resulted in the worst case, a meltdown, a hydrogen explosion, the release of radiation. And yet, nobody died from any of that. Inside the plant, there were a few dozen people that had higher levels of radiation exposure than one would like, and some of them may get cancer over time. Just talking about dozens of people. Outside the plant, where the public was exposed to elevated radiation, the levels of radiation never exceeded the levels that we set for medical or occupational exposure. Like you go in for x-rays, you go for MRIs, you work in a nuclear plant. We have levels of radiation that are considered safe, and you want to stay below those. The entire public around the Fukushima plant never exceeded those levels, and nobody died. Small amounts of radiation don't harm human health. And in fact, we live in a soup of radiation. It varies by as much as 100-fold from one location on Earth to another. It goes up when you take a transatlantic flight, or if you live in Denver at altitude, or if you smoke, or if you hang out in Grand Central Station, which is made out of granite, or if you eat bananas, which are slightly radioactive because of the potassium. Radiation up and down. We can track very small amounts of radiation. And it's true, radiation is still leaking from Fukushima into the ocean and making it radioactive, but the ocean's already radioactive. It's making it slightly more. And you can track a plume of radiation that came across the Pacific Ocean and threatened California after this accident, but the levels were so small, they were trivial. So that's the Fukushima accident. Actually, a great case for why nuclear power is so safe. Nature threw its worst at this plant, the worst happened, and nobody died. The 3 Mile Island plant in the United States, another big dramatic accident. Nobody died, nobody was harmed. It just had the bad luck to happen right when the movie, The China Syndrome with Jane Fonda and Jack Lemmon, was in the movie theaters, and everybody thought what they were seeing was probably Jane Fonda, about to die from a nuclear accident. The US Navy has a couple hundred reactors out on the sea right now. And they've been safe. The Navy has operated 6,000 reactor years to date without a single radiological incident. So nuclear power is safe. Then we have the waste, or as people say, the waste. We can't have nuclear power because we have no plan for the waste. This actually isn't true. The waste is completely misunderstood because the volumes, as I mentioned, are extremely small. Certainly compared with other industrial wastes, and definitely compared to coal waste. Coal produces 50,000 times the volume of waste, and we just dump it in pools next to the river, waiting for it to leak into the water supply and poison everybody. Nuclear waste is so small that if you used entirely nuclear power for your whole lifetime at an American style of electricity use, the waste would fit in a soda can. And in fact, if you took all the spent fuel from all the US nuclear reactors over the last 60 years and you brought them into one place, they would fit in a medium-sized Walmart. And this is the problem that people say, we can't use nuclear power to solve climate change because what will we do with the waste? We're talking about one Walmart out of the whole country of nuclear waste. What we're in fact doing with it today is we put it in swimming pools to cool off for a few years. And then we put it in casks out back, concrete dry casks out behind the plants. They're certified safe. They will be safe for decades into the future. They haven't had any problems. I've stood right next to these with no protection at all because radiation doesn't go through concrete. They're safe. After decades go by and we've solved climate change, we can either recycle these into new reactors that can burn them as fuel, or we can store them deep underground as the plan was to do at Yucca Mountain, but maybe we'll go back to that or some other place. Finland Finland is doing that now. Now, that brings us to the third critique of the trifecta. Nuclear power is dirty, dangerous, and expensive, according to the anti-nuclear propaganda. What I love about this is you can see all the coal smoke rising out of these nuclear cooling towers, which, of course, don't have any such smoke rising from them. So it's not dirty, it's clean, it is safe, but maybe it's expensive. So that is a serious critique and the proximal reason why we've stopped building nuclear power plants, mostly in the United States. Now, actually, the plants that we built decades ago were cheap, and they continue to be. So plants like Diablo Canyon or Pilgrim Power Plant, where I live in Massachusetts, the old ones are producing electricity below 5 cents a kilowatt hour. That's a good price. You're paying about 20 cents a kilowatt hour retail for electricity in California. And French electricity, which is 3/4 nuclear, is half the price of German electricity, which is a mixture of coal and renewables now. And in fact, how would you feel if I offered to build you a power plant for California that would power 1 million homes, carbon-free, at less than a nickel a kilowatt hour? It's a pretty good deal, but what if that plant also cost nothing to build and would last for decades, and if I could build it overnight to start generating electricity tomorrow? It's a pretty good deal, huh? Well, all you have to do is don't close down the Diablo Canyon nuclear plant. The old plants, the existing plants, they're cheap, they're reliable, makes no sense to close them. You Californians can figure out what you're going to do about that. What is super expensive, though, is the recent attempts in the US and Europe to build new nuclear reactors. These are first-of-a-kind designs built after several decades of not building nuclear plants, and often with changing designs and changing regulations while things are already being built, and they've gone wildly over budget. Here you can see that a typical gigawatt nuclear plant in the United States, the latest efforts is $12 billion to build that. And in Europe, it's 8 to 10 billion. And yet, in South Korea and China, Russia, that same plant would be $2,000. And the key in South Korea has been to build the same design repeatedly and bring down the costs over time. The same way you would do with any product that's very expensive, the first one off the assembly line, like an iPhone. The first iPhone off the assembly line, I think it cost $2 billion. And then, now we get it for $1,000 or whatever it costs. Costs have to come down, or the costs have come down in South Korea by building repeatedly on the same design. And this is what the French also did when they rolled out their nuclear reactors. Standardized design, repeated builds. The joke decades ago was that the difference between France and the United States is France has 2 kinds of reactors and 100 kinds of cheese, and in the United States, the situation is reversed. So better yet would be in a future build out of nuclear power, the reactors could be built centrally, the way we do with ships or iPhones, in factories or shipyards, rather than on site, each one unique, like building a bridge or a railroad. There you go. This is the Hyundai shipyard in South Korea, one of the advanced shipyards. And at volume, cranking these out in large numbers with shipyard or factory methods, you could probably bring that South Korean price down by half. And then you'd have a gigawatt plant for $1 billion, not 12 billion like our last attempt to do it. And you could generate electricity at 2 to 3 cents per kilowatt hour, which is cheaper than coal, cheaper than natural gas, cheaper than anything. And that's the game changer, because then that plant manager in Vietnam who's about to build a coal plant says, I'm not going to build that coal plant because I can do it cheaper with one of those newfangled nuclear reactors that they're cranking out off their assembly line and producing electricity for 2 or 3 cents a kilowatt hour. All right, so that's kind of theory, but let's look at what's actually worked in practice. My co-author always likes to say, if you want to know how to do something, look up on YouTube and find some videos of somebody who's done it before. And he's got, how to make fluffy pancakes or something. So how do you decarbonize an electricity grid really fast. And we need proven solutions that we know can work, and they have some advantage over theories and models that we're not quite sure how they're going to work in practice. So this book looks at places like Sweden, France, and Ontario, Canada, being Toronto, that have already successfully decarbonized with nuclear power. To decarbonize the electricity supply, the world needs to cut emissions per kilowatt hour. There we go. By about 90%. So the amount of grams of carbon going into the atmosphere for each kilowatt hour of electricity you're producing, that's the metric here. And the world is at about 500 grams per kilowatt hour, and we need to drop it to about 50. And this map comes from a wonderful website called electricitymap.org, electricitymap.org. And you can look up in real time where your electricity is coming from, what California is generating in the way of emissions per kilowatt hour. It'll show you over the course of a day the sources used to generate the electricity, et cetera. And they've color-coded it conveniently enough. So the high carbon methods of making electricity, like coal, are very brown. That would be, for instance, Poland on the map. Whoops, I'm not finding. Oh, that didn't work. You got Poland. Okay, you know where Poland is. Okay, so Poland is brown. Australia, very brown. That's coal. That's at about 800 on this scale. And then you've got Germany and California. They're about 200. And they're coming and going, sort of lighter brown and darker brown. Every once in a while, they flash green on a really windy day in Germany, a really sunny day in California. But most of the time, they're brown because Germany's using coal and California natural gas when the renewables are not producing. And then you've got the green ones, steady green. And they fall into two categories. There are countries like Brazil, Norway, New Zealand, Washington State, if it's shown up, there it is, that are using hydroelectric power. They're lucky countries. They have plentiful hydro resources. They've built dams, and they're producing carbon-free electricity that way. The trouble is that's not a model that you can extend to the rest of the world. Most of the places that can build hydroelectricity have already done it. There is some new build going on, especially on the Mekong River, but it's having pretty bad environmental effects, damming up the whole Mekong River. And there was a dam burst there that killed a number of people recently. But that's the hydro countries. And then there's a second category, Sweden, France, and Ontario. I guess that ran out. Got to the end of the year. Sweden, France, and Ontario, green year in, year out, all weather, day and night, and those are the nuclear power countries. They've already hit the target. They're already below 50 grams. So already less than 10% of the world average. And they didn't do it by sacrificing poverty. I'm afraid my clicker's not working, right? There it is. Okay. Sweden didn't do it by sacrificing poverty. Its economy got a big boost from the plentiful, cheap electricity when they rolled out nuclear power a few decades ago. The CO2 emissions per capita went down by 50% just in a couple of decades. And meanwhile, the GDP per capita went up in that same time. I visited Sweden's largest nuclear plant at Ringhals, where they have 4 reactors by the ocean, and it's not a scary place, it's rather a nice place. It disrupts the environment so minimally that you would never know that it's enough electricity to power a whole city from that little plant. And most importantly, nuclear power can scale up very rapidly, which is exactly what we need now to solve climate change. When France decided to switch from fossil fuel to nuclear power, they took the fossil off the grid and replaced it with nuclear power, the whole country in just 15 years. 15 years, decarbonized, got rid of the fossil fuel. Meanwhile, Germany has talked the talk about decarbonizing a lot. It's had very aggressive goals. It's had political support across the board, something that few countries have, and lots of money and lots of technical expertise. They've had this Energiewende policy for the energy transition, which is supposed to green up Germany. But their carbon emissions have hardly changed. And that's the metric that matters. Not how much you talk about decarbonizing, not how many people you turn out into the street demanding action, not how many renewables you install. It's your carbon emissions that really matter. And they barely decreased. And in fact, most of the cases of adding clean electricity quickly to the grid, these are the fastest ones at the left in the world, have been nuclear power, those blue bars. You have to go out a ways to get to Bulgaria, which relative to its GDP added solar and wind pretty fast. Not as fast as South Korea and Sweden did, though, relative to their GDP. Germany and Denmark, we've added at the right side of this graph. They're not even in this top 10, top 15, but we put them in for a point of reference. The bottom line, if you follow Germany's model of building out renewables relative to GDP, it would take 1.5 centuries to decarbonize the world economy, the electric grid. But with France's model, you could do the same thing in 30 years. So 5 times faster with nuclear power than with renewables. And looking again at this measure on the vertical axis of grams of carbon per kilowatt hour, that's called carbon intensity of electricity generation, it's been flat. It's been flat since 1990 when we first started signing these treaties on climate change. And if we didn't add any new low carbon sources, it would rise because our existing low carbon sources would be a smaller amount of the mix as electricity demand goes up. If we followed Germany's energy transition model, the one we were just talking about, it would be flat. We wouldn't ever decarbonize. And if we just, part of that's not fair because Germany has been closing its nuclear plants while it's building renewables, and you only close your nuclear plants once, so let's ignore that and just look at the rate at which Germany is adding renewables. And if you just do that, then it's coming down. But it's coming down so slowly, we'll just never get to decarbonization in time. Far too slow for mid-century. And if we look at Germany's best 3-year period, which by the way is not the last 3 years, but some years before that, their best peak rate of adding clean energy, it still would only get halfway there by mid-century. But if you look at France's rate, we would get there by mid-century. And my Swedish co-author always likes to point out that with Sweden's model, you could do a little better than France. If we apply the same kind of projections to the United States, again, normalized for GDP size, the green line would show the expansion of wind and solar combined, take most of a century to get to 0. And at the peak US nuclear build rate, the rate that we used to build nuclear reactors before we stopped doing it, relative to GDP, if we just repeated that now, that would be the yellow line, and we would reach 0 before 2050. And if we did the French rate, which is the red line, we would go much faster even than that. Now, the most important country in the world is China, because it has more carbon emissions than the US and the European Union combined. And China currently leads the world in the construction of new nuclear plants, but not nearly enough. I think they have between 15 and 20 under construction now. China could reduce the world's carbon emissions by more than 10%, the world's total by more than 10%, in less than 20 years, just by building nuclear power plants massively and displacing coal off of their grid, French style. They would need about 650 gigawatt reactors in 15 or 20 years to do that. And they know how to do that. They know how to keep the costs low. And they have built these AP1000 Westinghouse designed reactors. The same thing we're in the United States trying to build in Georgia. That's that $12 billion thing that we can't seem to get built, and it's still not finished. They just put 4 of those exact same reactor on the grid in the last year. So they can build them. They know how to do massive infrastructure projects. Should get them to build your California high-speed rail while we're at it. And then as China did this, building hundreds of reactors to displace coal, it would also create the designs and production methods to help the rest of the world do likewise. So with this kind of approach, we can solve humanity's greatest problem, starting in China and going on to the new generation design reactors that are being developed now in the United States. the US design reactors would be centrally built. This is a small modular reactor concept built in a factory and delivered by truck from NuScale, an Oregon company. They're working on that now. And my favorite is actually built in shipyards and floated to its destination. Most of the cities in the world are coastal, so build them in shipyards, float it out to the city where it's going. And while you're at it, put hundreds of them on the oceans to de-acidify the oceans and suck the carbon out of the ocean so that it'll pull it out of the air to replace. Ideally, we're going to need about 1,000 new nuclear reactors every year worldwide. That's a lot more than I have in the book because my thinking keeps evolving. I keep realizing we need more clean energy. 1,000 a year for 25 years, we could actually do all of those things that I said at the beginning of the talk. Sequestering from the atmosphere, giving air conditioners to India, all of that stuff. And to do that would be roughly equivalent of the world's jetliner industry. So the world makes about 2,000 jetliners a year. I'm talking about 1,000 nuclear reactors. A jetliner is a couple $100 million per. I'm talking about building these for $1 billion, maybe get it down to some hundreds of millions. So it's a little more than the capacity of the jetliners in the world, but not that much more. You produce them for a gigawatt at a gigawatt reactor for $1 billion or less, and you generate electricity for 2-3 cents a kilowatt hour. The total investment worldwide would be about $1 trillion a year. But that's not an expense, that's an investment. You get most of it back from selling the cheap electricity, displacing fossil fuels, and someone will actually make a lot of money doing that. So by gearing up quickly to build new reactors at that rate, if we can overcome our fear and our political inertia, we can actually create this bright future for the world and solve humanity's greatest problem. And I have more information in the book, and there's also a website at brightfuturebook.com. So let me take questions now. Thanks.
So Joshua, it would seem to me that job one would be to stop closing down the plants that we do have. Is there an effort that you see gaining momentum to keep some of those plants operating?
There's some effort that's gaining momentum to keep plants operating that are operating. Diablo Canyon is a good example of it, and we have one in Massachusetts, the Pilgrim plant, that's going to close this June. When it does, it will take out more clean electricity generation than all wind, solar, and hydroelectric ever built in the history of Massachusetts. So all the efforts that the environmentalists have made will be wiped away in one day when they take the power plant off the grid. So that's crazy. And there are efforts in several states like Illinois, New York, and a few others still ongoing to create some incentives to put nuclear power more on a level playing field with renewables. And specifically, many states have a renewable portfolio standard that tells the utilities you must have X amount of renewables in your power generation mix. So by changing that to a clean energy portfolio standard and including nuclear power along with renewables, that puts nuclear on an even footing with the renewables. And they've been able to keep reactors open that way. So that's part one of the answer. But part two of the answer is, in another sense, I don't really care about all these reactors because there's not enough of them to matter. We need to be doing the new thing. We need to be forward-looking towards, I'm talking about building 25,000 reactors. So whether Diablo Canyon is there or not doesn't really matter. And if you think about the world of 2050, most of everything that's out there now will be gone. All the solar and wind will have aged out by then. Most of today's nuclear plants that were built in the 70s and 80s will be, if not aged out, near the end by then. All the fossil fuel, which is 2/3 of our generation, will by definition be gone if we've decarbonized. And you'll have a few hydropower plants still going and so forth. But basically, we're creating something new from scratch. And the backbone of it has to be nuclear power, and it has to be produced en masse, as I've been talking about. And in that world, what happened to those old plants will be really secondary. So I wouldn't want to get all hung up on that. Like if we can save a few of these old reactors, we'll have solved the problem. That's not how we're going to solve it.
Are you optimistic, though, that we will do what you're proposing?
I'm pretty optimistic. I think that the hard part of it is you need a lot of capital up front. I'm talking about $1 trillion investment per year. And it's very hard in a deregulated market to get investors to put money in for something that's going to pay off for 60 to 80 years down the road. So in the places it's been successful, there usually is a strong government support for the program. And I think we're going to need that, sort of an Apollo project, bigger than that, though. Manhattan Project, Apollo Project, you know, the World War II kind of mobilization for all these climate things. But this would be a core piece of it, to where the government would provide capital, funnel resources, stimulate the innovation, and then turn it over to private companies to actually build the things.
Who has a question or comment? I'll bring a microphone.
Okay, so I'm a big fan of nuclear power. I was 6th on the list to go clean up 3 Mile Island. I'm not so much a fan of small nuclear power plants because they're hard to defend. And the one thing that's different about how a nuclear power plant is dirty versus how a coal power plant is dirty is that if you took the truck train full of coal dust and spread it over a city, some people would get sick and a lot of people would get smudgy. But if you took the soda can full of nuclear waste and blew it up over part of a city, it'd be really hard to clean that up to any good level. Although if you put it very well distributed, it wouldn't be that much of a problem. But bigger nuclear power plants are defensible from anybody wanting to come steal stuff and do nasty things with it.
Yeah, so 2 pieces to the answer to that. One is the idea of spreading nuclear material around in a dirty bomb and contaminating a city. It's a psychological weapon. The amount of radiation is actually not going to hurt people. It's just going to freak everybody out and disrupt everything, which would be very expensive. If I were a terrorist looking for material to do that with, I wouldn't go to a nuclear power plant. I'd probably go to a hospital or somewhere else that's using nuclear material because they'd be a softer target. And you don't need a lot of it because it's just going to create the psychological impact. You're not actually making enough to try to hurt people with radiation. And the radiation does disperse. And in general, nuclear power plants are not a good terrorist target. You know, people imagine flying planes into them and stuff like that. You're laughing because the containment vessel is made out of concrete and the plane's made out of, you know, this thin structure, and it would just disintegrate. They did studies of this after 9/11. So that
They did studies of that. I remember that when 3 Mile Island went down.
yeah.
Could have been hit by a 747, fully loaded at full speed.
Fully loaded 747 hits a nuclear power plant, plane destroyed, nuclear power plant, okay. So that's not the worry. And the idea that terrorists are going to get nuclear material, I didn't talk about proliferation, but I want to for a second right now. Terrorists getting nuclear material and making a bomb out of it's really fanciful. It's extremely difficult to do, takes a lot of money, a lot of people, and even if you could get the material, it wouldn't be in the form that you needed. A country could do it, but countries that have made nuclear weapons haven't done it from civilian power plants. North Korea doesn't even have civilian power plants, neither does Israel. Pakistan has them, but it has 2 separate programs, one for civilian power, one for making plutonium for bombs. It's more efficient that way. So that's not really the concern. And nuclear power around the world so far has not contributed to proliferation of nuclear weapons in any meaningful way. We have strong institutions, international systems, the International Atomic Energy Agency, IAEA. They go in and monitor all the nuclear industry sites, and they put in cameras and seals and keep track of everything. It's worked well so far. If you were to expand nuclear power the way I would like to, you'd need to strengthen those systems. And you do want to keep an eye on it. But so far, it's worked, yes.
Well, feed you a question. How well can the IAEA monitor nuclear isotopes over the face of the planet?
The IAEA, the question is how well can IAEA monitor nuclear isotopes over the face of the planet? Pretty well, I think.
They can detect a grain of rice spread evenly over the entire planet.
One grain of rice spread evenly over the planet, the IAEA can see it. I have a picture in the book of the IAEA installing these cameras. I mean, so this system is working. Then again, if you're expanding a lot, you want to pay attention to how to keep the fuel cycle from leading to proliferation. So far, the big factor of non-proliferation is most countries that could make bombs have decided they don't want to make bombs. Countries like Brazil and Argentina that started down that road said, this is pretty stupid, and they stopped it. South Africa made a bomb and then got rid of it. Sweden was once going to make nuclear bombs. And the nuclear power industry actually helps, because when you come to get nuclear power, you join up with the IAEA and you get these controls, and it makes it harder to make bombs. So you sort of, and that happened with South Korea. They were thinking of making a bomb, and they're like, no, we'd prefer to make electricity, and that ruled out the bomb route. Now, one more piece of this, and then we'll get another question, is the bigger plants being better than the smaller plants. I wouldn't say so much because of the defensibility, but economically, bigger plants have been cheaper per kilowatt hour. And some of these new small modular reactors, like the one I showed on the back of the truck, they're great, except so far, they've been too expensive per kilowatt hour to suit my tastes. But putting one of the big ones on one of the new designs, floating on a barge and made in a shipyard, then I start to perk up on that.
One in the back, and then up here.
I wanted to say that I really
Hold the
like-
microphone closer, please.
Okay. The title of your book, A Bright Future, I really like the title. It's very inspiring. And when I look at all the young people that are here this evening, it really touches my spirit to see you here, because you're the future, and I know that you really, really, really do care about our environment. So I want to say kudos to all of you. I was going to ask about the education, because there's so much confusion with nuclear bombs and nuclear reactors. And I want to ask also that Sweden and France are doing so well. Has the United States thought about bringing them here for them to take care of what we need done and just pay them, since they're able to do it more economically feasible, and they seem to have a little bit more, and I'm going to use the word intellect or insight. Is that a possibility so we can move forward?
There is cooperation among nuclear energy engineers and all operators across international boundaries, so there is some of that cooperation. I think it's the South Koreans that you'd bring here. They've already exported that plant that I showed you. Is called the APR 1400, and they exported that to the United Arab Emirates. And they have it under licensing review here at the Nuclear Regulatory Commission in the United States. It's been sitting there for 4 years, waiting to get its approval. But that's a plant that's been built and licensed and exported, and they could come here and build them for us. But politically, it's a difficult problem to, ask another country to come and do what we invented in the first place. Although, we are buying a lot of stuff. Yeah, go ahead.
Yeah, that's a good point. We invented it, and we ship it out, but we never got it back. When you're talking about aging power plants, can't the plants themselves upgrade and in-house? Especially a large facility could set aside room to set up a newer plant as technology changes, and then rehab, and work back and forth.
Yeah.
So when we talk about these aging power plants like San Onofre and up there, Diablo, they don't really age out. I mean, just like any power plant right over here in Seal Beach, they're just rehabbing them.
Yeah. Point well taken. They usually license extensions 20 years at a time, and nobody knows how long that could go. But some of the old plants are still operating fine. They upgrade them, just as you said. And so when I said most of today's plants will be pretty old by then, by 2050, most of those plants will be 80 years old. Now, would the 80-year-old plant still be upgradable and working, or would we have something better by then? I don't know exactly, but yeah, they can go for a long time. And a plant like Diablo Canyon, that's a perfectly good plant that could go for decades more into the future. So they don't age out in that sense.
I think, education really is key. And Ben, we really appreciate your bringing your students here. Maybe you could check tomorrow in class and see whether they've changed their opinions and where they come down on nuclear. Go ahead.
Hi. Since the 1950s, we've had this, our proliferation of the United States nuclear power plants. But neither the federal government, nor any of our state governments, nor any of the R&D places, nor James Hansen, nobody is figuring out what to do with the waste. And so here in California, we have Diablo Canyon and we have San Onofre, and they are just piling up nuclear waste on the beach when we're all facing incipient sea level rise, and they're all both on earthquake faults. And I'm just really frustrated that since the 1950s, nobody has a solution of a safer place to put the waste, not on the beach. SoCal Edison has 27 canisters on the beach at San Onofre, and I want to see it moved off of the beach before we get a tsunami or an earthquake. And nobody has an idea of what to do after, we squelched taking it to Nevada. Nobody has stepped up and said, well, what are we going to do with the waste?
So
Go ahead, Joshua.
it's not true that nobody had an idea. We had a whole national program to figure out what to do with the waste and decided on this Yucca Mountain facility, sunk some billions of dollars into building it, and then for political reasons, it got squelched. It's still sitting there. It may still reopen. It's a perfectly good solution. It's what Finland is doing with their waste. Bury it deep underground. Now, it's true, there are elements in that waste that have very long half-lives and will be radioactive for a long time, but compared to the industrial wastes that we just dump down wells every day, they have half-lives of forever. Mercury, lead, arsenic, cadmium, those are all toxic things that we just dump and they're there forever. So radioactive waste has the advantage that at least it gets less toxic over time. Finland is building the first actual functioning repository. They're constructing it now. And Finland did a study of what could go wrong if everything went wrong with this repository. The casks that we're putting the waste in are already cracked before we ever put them underground. They're falling apart. The clay layer that's packed around them, that all magically dissipates. And 1,000 years from now, somebody lives their whole life on 1 square meter of ground, right above the waste, getting all their food and water from that. How much radiation would they get? And the answer was about the same amount as eating a bunch of bananas, which are slightly radioactive. So this idea that any amount of waste, anything that goes wrong with the waste is some great hazard, it isn't. We've dumped a lot of radioactive waste in the ocean. It dissipates in the ocean. It doesn't concentrate. And that's not a good way to handle it. We have better ways than that. We've got a lot of waste sitting out in the casks out behind plants. It's safe. We've never had an incident with it. Yes, you might have an earthquake and some cask at San Onofre something might happen to it. But this idea that because something in the future might go wrong with the nuclear waste, and it might even harm some people. Let's say 100 people get cancer and die because some cask, gets washed up with a tsunami and breaks open. So I just told you, 1 million people every year die from coal. So is this a reason to not take coal off and replace it with nuclear power? I don't think so. The casks at San Onofre haven't hurt anyone. I don't know what else I can say. If you're going to compare nuclear power to fairy dust, that nothing ever goes wrong and it never hurts anyone, then you're never going to build any nuclear power. Then you're going to keep burning coal. That's exactly what we're doing. And I want to say to the young people, that's what our generation, my generation, back with my long hair and my beard, we set this in motion. We don't trust nuclear power. There's nothing to do with the waste. It's too dangerous. We don't like it. We confuse it with nuclear weapons. And we set the world on a course that you, young people, are going to live your lifetimes and your children in an uninhabitable world of hundreds of millions of people dying in droughts and floods and heat waves because we considering ourselves environmentalists, thought it would be unnatural to use nuclear power. And you, young people, should be rethinking that and demanding a change from us oldsters. Okay.
I'm still a little fuzzy with nuclear, and so I was just curious to know, is there, obviously a lot of these nuclear places are set near some water, and so is water being drawn from the general area to kind of cool down, and then does that water come back out into that same body of water?
Yeah.
Okay, and if so, do you notice like a change in temperature from when it goes in versus when it comes out? And if so, how does that affect the nearby like marine or aquatic ecosystems?
Yeah, so for instance, the Swedish power plant, you're exactly right. It's built next to a lot, the ones with the big cooling towers that you think of as nuclear plants, those are away from water, but most of them are near water because it's cheaper and easier to cool it from a water source. So the Swedish one's on the ocean, the one in Massachusetts that was near me that closed down was on the Connecticut River. So I visited the Swedish plant. They pull the water from the ocean. It warms up by about 15 degrees, and then it's discharged into the ocean. And it does create a zone of warmer water. More fish grow there. The locals would say, oh, well, we love to fish in the plume from the nuclear plant, because, and they like to swim in the plume from the nuclear plant. It's like warm water is a good thing if you live in a cold place. But it makes some changes, but I don't think they're always bad changes.
No, so those are once-through cooling systems where you take the water out, cool the condensers, and then discharge it at an elevated temperature. Probably the worst plant I know of was designed, it's Chalk Point near the mouth of the Patuxent on Chesapeake Bay. And it was taken away from the physical scientists and the engineers. And the argument was, we want the water to cool down before it goes back into Chesapeake Bay. So they built a long canal. And it didn't cool it down at all, because the only way you get the water temperature come down is by mixing it with other water. And that was the worst one I know. I want to see if others who haven't had a chance. Yes, Ben.
I might give it a try without the mic. Do we I suppose that this question is in part addressing the public relations result, since you were a 19-year-old and about that time. Do we not have, does the United States not have a functioning nuclear waste recycling facility in South Carolina that's proven to work? Is that no longer the case? Is that on ice? But it was operating for a while.
From civilian nuclear waste or military nuclear waste? We have a whole...
Both was my understanding, and that due to NRC and that the cobwebs that is their line of work, out of necessity, it just was not enlarged. It was not taken to any scale, obviously. So this would be alternative to Yucca Mountain in a way. Would not doing what France has done for decades and repurposing that change the linear metabolism mindset of those who don't embrace nuclear at all,
right,
as opposed to kind of closing a bit of the loop?
Yeah, so closing the loop is to take the fuel that now goes once through the reactor and still has 90-some% of its energy intact, and then we're going to put it underground, but instead to put it through and get that energy again. So that can be done with breeder reactors, and you process it, reprocess it, and put it back into the reactor. And France does this. It's called closing the cycle, fuel cycle. And some of the new reactors, the fourth generation reactors, like Bill Gates's TerraPower first reactor design of the two they're working on, was going to do that. It has some disadvantages because you are separating out plutonium, and then you get, talk about 25,000 new reactors and all kinds of plutonium floating around. It complicates it. So that may be a way to go. I'm not sure. It may be the once through thing is the way to do it. It was originally created our breeder reactor program, which I think President Clinton shut down many years ago, was created because of a concern that uranium supply would run out. We wouldn't have enough uranium, and so we needed to reuse it. And since then, we seem to have plenty of uranium. Maybe not enough for the scale that I'm talking about, although you can get it out of seawater. So there's different ways to do that fuel cycle, and I'm not the technical expert. That's my co-author. He's a nuclear engineer. But that's my understanding.
Okay, you go ahead. This is
Hi.
gonna be our last one.
My question is, what is the current progress on thorium molten salt reactor technology, and is it viable?
Yes. Thorium and molten salt, actually two different things, but they can go together. Thorium is a fuel that you can burn instead of uranium. It's not quite true. You actually blanket and turn it into something and then burn it and so forth. But let's just say it's an alternative nuclear fuel to uranium. And going back to Rickover, Admiral Rickover created the light water reactor, things that we're using mostly ever since. But Alvin Weinberger wanted to use thorium, and there's a whole book about it called Superfuel. Richard Martin, it's pretty interesting. And there are people colloquially known as the thorium heads who are like big advocates of thorium and think that this was, we made a mistake to go the uranium way. We should be running everything on thorium. There are places, India has a lot of thorium and not much uranium, so they're very interested in thorium reactors. But basically, you can run a reactor on either of these fuels. The molten salt, I think, is a lot more interesting, I think, than the thorium versus uranium question. And the molten salt reactor is one in which, if I can do this quickly, right? Right now we use solid fuel rods, and it's got the uranium in there. You put them close together, they get close enough, they create a chain reaction and so forth. You can pull in and out moderators to control the reaction. So in a liquid-fueled reactor, molten salt, the uranium is in a liquid of molten salts of some kind. There's a couple of designs. And so it's creating the chain reaction in this liquid. And it has some inherent design advantages, especially for safety, because if anything goes wrong, it doesn't melt down the way the solid fuel does. And it's got some advantages for proliferation, and hopefully has some advantages for cost. So one of the companies so there are a number of these startups right now in the United States and Canada that are working on molten salt reactors. Terrestrial Energy is one. That's a Canadian company. They're pretty far along. And Kairos Energy out of Berkeley. And the one I kind of like that's a little under the radar is Thorcon. It's a thorium-uranium molten salt reactor. But what's interesting about the company to me is it was created by shipbuilders who have just decades of experience building ships, large, complex container ships and tankers in these shipyards, and how to shave the costs. So they want to do with molten salt thorium-uranium reactors what shipyards do with these large, complex container ships. And that's a great model to be able to float them to site. They've got a whole deal going, and they've got a contract, I think, now with the government in Indonesia to start rolling these out in Indonesia as their first customer. But they're undercapitalized. So if you know anyone with a lot of money that wants to invest
Bob,
in
you
molten
get
salt,
the last one, a nice short question that could be answered with a yes or a no or a maybe.
Yeah, I won't do my jury impression. I'll make it short. Hot water or warm water being released into the sea is not unique to nuclear energy.
Right.
Right over here we have Ray Bay. The water comes down out of the power plants, and that's where you wanted to surf on the Seal Beach side of the jetty, because you could surf in warm water. So that's not unique. That's any power plant that generates energy.
any thermal reactor, coal, gas, or nuclear, they all release warm water. It's exactly the same. Nuclear power is just a different way of boiling the water. Yeah.